actually discussing third order nonlinear effects. That is brought about by this term epsilon 0 chi 3 e cubed. This is the first nonlinear term that is present in media in which there is a center of inversion symmetry, which means all the second order tensor elements are 0, and media like glass or liquids, they have this first nonlinear term in the expansion. So we started looking at the effect of this term, and let's recall that the first thing we looked at is if I have a medium possessing a chi 3 value and I launch light at single frequency omega, then I found that the electric field as a function of z goes as 1 by 2 e of 0 exponential I k plus omega by c n2 I into z minus omega t plus complex conjugate e of z in time, actually z and t. The electric field as a function of z and time for an incident electric field of the form exponential I kz minus omega t, as it propagates through the medium, the electric field gets modified, and what effectively is happening is the refractive index changes from n0 to n0 plus n2i. The propagation constant has changed from k to k plus omega by c n2i. So effectively, if n0 is the refractive index of the medium for low intensities, the intensity of the medium at high intensity becomes n0 plus n2i. n2 is the nonlinear coefficient, and as I mentioned to you, for glass, it's about 3 10 to the minus 20 meters square per watt. This is for silica. So glass fibers are made of silica, and that's the typical value of N2. And what we also found is that the change in index is very, very small. But if you propagate over long distances, the accumulated effect of the change in phase can become significant and comparable to pi, which means essentially you can go from, in interference terms, you can go from constructive to destructive interference. So this term leads to what is called as self-phase modulation. Self-phase modulation, or SPM. And this is very important in experiments in optics in which the intensity becomes quite high and you're propagating through media over long distances, or if you have a very small cross-sectional beam with a reasonably high power, then the coefficient, this term can significantly affect light propagation. Now, although this analysis is valid for a monochromatic input at a single frequency, I can use some heuristic arguments to tell you what will happen if I had a pulse of light incident in such a medium. Pulse means the intensity is not remaining constant, but changes with time. Now, although this analysis has assumed monochromatic waves, I'll try to argue it heuristically and tell you what is the effect of having an intensity-dependent refractive index on a pulse of light that is launched into this medium. Now, in this case, what will happen is this I will not remain constant with time. I itself will change with time if I have a pulse. For example, if I have a Gaussian pulse of light, the intensity increases and decreases with time, which means the intensity at the input increases and decreases with time, which means that the output phase also changes with time within the pulse. So the phase change now, the total phase change will become like this. Phi will be k plus omega by c into I into z minus omega t. This is the phase at the output which is at z as a function of time. And so if intensity is a function of time, this is omega by c into n0 plus omega by c n2. This is a function of time into z minus omega t. Now, this is a term that means you have a function of time now at the output which is not exponential I omega t, but it has another time dependence. So, suppose I have a pulse which varies as exponential I phi of time. I define what is called as the instantaneous frequency. Instantaneous frequency as omega of t is equal to d phi by dt. The rate of changes of phase with time is defined as instantaneous frequency. If the phase changes linearly with time, if phi of t is omega t, then d phi by dt is omega, the frequency, which remains constant with time. If phi of time is not a linear function of time, then d phi by dt is not a constant, and the frequency, instantaneous frequency of the pulse will change with time. That means within the pulse, the frequency does not remain constant. Have you heard of a pulse like this? What is such a pulse called? Chirped pulse. The frequency within the pulse changes with time. This term comes from bird calls which chirp. The birds chirp. So there is a frequency which varies with time. And that is essentially a situation here where the frequency of the signal is not constant within the pulse, but changes with time.
In general, in any pulse, we say that there are multiple frequencies present in any finite duration pulse.
Yeah.
So how is it different from that case?
Okay, now let me show you two kinds of pulses. One, for example, I can have a function of time which is equal to, so electric field. So let me write electric field as a function of time is equal to E0 exponential minus t square by tau 0 square exponential minus I omega t. Now this is a pulse. If I were to draw the real part of this equation, the electric field will look like this. This is the envelope, and inside there are the oscillations. Because what I'm plotting is E naught minus t square by tau 0 square cos omega t. Now this is an amplitude term, and that is a phase term. The instantaneous frequency within the pulse is constant because the phase term is omega t, exponential minus I omega t. Frequency remains constant with time. But this pulse contains many frequencies. Because if you take a Fourier spectrum of this pulse, if you take a Fourier transform, you will find that this pulse contains many frequencies. What will be the spectrum of the frequencies? Of the order of? So delta omega, 1 by tau naught. Narrower the pulse, the broader the spectrum. The broader the pulse, narrower the spectrum. This is a Fourier transform pair. The function of time and the function of frequency, which are Fourier transform pairs, they have an inverse relationship in bits. So this is kind of an uncertainty relationship. You cannot talk of a very narrow pulse with a very narrow frequency spectrum. It's not possible. The moment you define tau naught, the width of a pulse, the duration, you have no choice as far as delta omega is concerned. There is a minimum delta omega. So this is called an unchirped pulse. If you had a function of time which was E0 minus t square by tau 0 square exponential minus I omega t plus phi of t, the envelope is still Gaussian. The intensity varies still as intensity means proportional to square root of E, mod E square. So it is still proportional to exponential minus 2 t square by tau naught square. the intensity varies in a Gaussian fashion, but this one has now a phase term which is also a function of time apart from an omega t dependence. So the instantaneous frequency of this pulse is not constant with time. This is also a spectrum, and this spectrum is not related, it's not given by this equation. This equation is valid for what are called as Fourier transform limited pulses. Delta omega tau into tau naught is greater than or equal to 1. It is not always equal to 1. I cannot have less than 1. So all it means, this pulse has the same width, but has a spectrum which is much broader. If you take a Fourier transform of this, for example, if phi of t happens to be, say, alpha t square or something, okay, some function which is not a function of linear function of time, alpha t square or something else, then you can show that the spectrum of this pulse is broader than the spectrum of this pulse. Both of them have the same width. If you were to detect both the optical pulses, they will give you the same intensity dependence versus time. They will give you the same electrical signal because the detector responds to intensity. Intensity of this is proportional to mod E square. So intensity of this and intensity of this vary in the same fashion with time. So a photodetector will give you the same current variation with this and with this. But if you were to pass this through what is called as an optical spectra analyzer, which means it gives you the optical spectra, what are the frequencies, optical frequencies present in the medium. For example, a grating. If I were to push it on a grating, the grating spreads out the various frequencies. You will find that the frequency spread of this is smaller than the frequency spread of this. So a chirp pulse always has a frequency spectrum which is broader than the corresponding unchirped pulse. And that comes about simply by a Fourier transform relationship. If you take a Fourier transform of this, you will get a spectrum of the order of 1 by tau naught, width of the order of 1 by tau naught. If you take a Fourier transform of this, it will always be bigger than 1 by tau naught. So for a given spectrum, the narrowest pulse you can make is given by 1 by delta omega, of the order of 1 by delta omega. So suppose I give you a spectrum over a certain frequency range. I have light at the frequency range, delta omega. The shortest pulse you can make with this spectrum is of the order of 1 by delta omega. You cannot, with this spectrum, you cannot make a pulse which is 1 by 10 delta omega. I cannot make, because they are inconsistent with the Fourier transform relationship. I can have a broader pulse with the same spectrum. I can't have a narrower pulse. So this is the delta omega into tau naught is greater than of the order of 1. Exactly like an uncertainty. It's an uncertainty relationship, actually. So that's the difference between the moment you have any time dependence other than exponential minus I omega t, it has a spectrum. This has a spectrum, this has a spectrum. In this case, what is actually happening is within the pulse, the frequency remains constant. Instantaneous frequency does not change with time. Here, the instantaneous frequency is changing with time. Okay, so this is different. This is called the chirp pulse. This is called an unchirped pulse. And this is a Fourier transform limited pulse because the spectra and the temporal duration are related to delta omega into tau naught of the order of 1. This one will have a delta omega into tau naught greater than or equal to 1, greater than 1. Okay, so now what's going to happen is, in our case, with cell phase modulation, what I see is at the output of this medium, the phase is varying with time, not linearly, but with some arbitrary function of time, into I of t here. So I can calculate from here an instantaneous frequency by just differentiating phi with respect to time. And what is instantaneous frequency I will get? So let me call this omega tilde of t is equal to This is the differential of this. So this is omega by c n2 di by dt into z minus omega. What is omega? Omega is the frequency of the input pulse. This that's center frequency. Okay, the input pulse varied has exponential minus I omega t. So let me plot. For example, if I had a pulse like this, this is I as a function of time. I must define it with a negative sign because I'm defining exponential minus I omega t. So please define it with a negative sign here. So the frequencies are always positive. So this is actually this. Because of exponential minus I omega t here, the frequency of this is omega. So I must define as minus d phi by dt. Okay. If it was exponential I omega t minus kz, I would have defined d by dt of omega t. This is to get the correct expression. If I had minus I omega t, then I would have to call as minus d phi by dt. Okay. So now you see here. If I plot di by dt, so di by dt is positive here, di by dt becomes negative on this side. This is di by dt. Differential of this I as a function of time. So what does it imply? So this is the center of the pulse. Look here, this is the center of the pulse. So at the center of the pulse, di by dt is 0. And the frequency, instantaneous frequency is omega. The same as the frequency of the input. This side corresponds to the leading edge of the pulse. Please remember, this is earlier time than the center. So this is not plotted as a function of space coordinate, it is being plotted as a function of time coordinate. So this is earlier and this is later. So this is the front of the pulse. And this is the back of the pulse. Because if you are standing at some point, you will start to see from here. The first one to arrive will be here, then this, and then this. So the leading edge has di by dt as positive, which means the instantaneous frequency is lesser than omega. And so the leading edge, this is the leading edge. And this is the trailing edge. So the leading edge has an omega tilde less than omega naught, omega, and this has omega tilde greater than omega. So what will happen is, if I were to draw this pulse, it will look like this. You have now I've drawn a lower frequency here, omega here, and a higher frequency here. The oscillations are faster here, slower here. This is omega naught, omega. This is less than omega, and here it is greater than omega. And this is a chirp pulse. Now the way we have analyzed this problem is, what is happening is the pulse enters the medium and comes out with the same width, but now chirped. So as I mentioned to you, if you have two pulses of the same duration, but one is chirped and one is not chirped, the chirped pulse has a higher frequency, larger frequency spectrum than the unchirped pulse. So what is actually happening is, the self-phase modulation chirps the pulse that is propagating through the medium. So the self-phase modulation actually leads to the generation of new frequencies. And that is coming because of nonlinear effect. Yes, Mohit?
Sir, in this chirp pulse, we have I mean, earlier we say that the frequency of this pulse is less than omega, then it becomes constant at omega, which is the incident frequency.
No, instantaneous frequency is constant with time, but that input pulse has a spectrum. There are frequencies present in the input pulse over a spectrum width of the order of 1 by tau naught. So suppose I take a 1 picosecond pulse, it has a spectral width of the order of inverse of a picosecond, which is 10 to the 12 radians per second. Now what I am saying is, the output has the same 1 picosecond duration, but now it is chirped. So its spectrum is not inverse of 1 picosecond, but more than that. So if I start with a 1 picosecond pulse, if I start with tau naught, input has a spectrum of the order of 1 by tau naught. The output has the same width, tau naught, but has a spectrum which is more than 1 by tau naught. That means self-phase modulation has led to the generation of new frequencies within the medium. And those new frequencies have been generated primarily because of a nonlinear effect. We have seen nonlinear effects generate new frequencies. So this new frequencies that come out is actually because of the nonlinear effects within the fiber, and the spectrum of the output is now more than the spectrum of the input. So we can actually estimate the increase in spectral width by a simple argument. So let me calculate what is the spectral width increase. Yeah.
In terms of photons, does it mean that 3 photons combined to make a?
Yeah, they have all mixed together to create new frequencies. Some photons have disappeared from some. The total energy will remain the same. If I assume there is no loss in the system, whatever energy you have put in will be coming out from the medium. The only difference that is happening is the frequency spectrum is different. It's exactly like in second harmonic generation, whatever energy you are putting in is coming out, either in omega or in 2 omega. Similarly here, you have put in a certain spectrum of frequencies at the input. What will come out is a broader spectrum of frequencies by mixing of energy into various new frequencies. So new frequencies have got generated by taking of energy from the other frequencies. So it is leading to some and all kinds of mixing of these frequencies. Okay, when we come to putting more input into this nonlinear medium, we will see that how the new frequencies can get generated. Okay. Okay, so let me calculate what is the typical. Let's put some numbers and calculate. Okay, so let me rewrite this equation. Omega tilde of t is equal to omega minus is there something wrong in the equation dimensionally? That's fine. Okay, this is length by time. Length cancels off. This is time goes up. Okay, this is fine. Yeah. Okay. Now let me take some typical examples. So I is equal to, let me take a Gaussian pulse minus intensity varies. This is called a Gaussian pulse. This functional dependence is a Gaussian. And so this means that the intensity increases and decreases like this in a Gaussian fashion. So di by dt is equal to minus 4t by tau naught square I naught exponential minus 2t square by tau naught square. So I can substitute di by dt into this equation and find out the instantaneous frequency as omega tilde of t is equal to omega plus omega by c n2 z into 4t by tau naught square I naught minus 2t square tau naught square. This minus sign with the minus sign here becomes plus omega by c n2 into z into 4t by tau naught square I naught exponential minus 2t square by tau naught square. So as you can see here, the center of the pulse is t is equal to 0, and this, because of this factor here, omega tilde becomes omega, and the leading edge of the pulse is less than t less than 0, so this is negative, so the frequency is less than omega. The trailing edge of the pulse is t greater than 0, which means this is positive and the frequency is higher than omega. So instantaneous frequency is the frequency is increasing with time. You could also have a chirping which the frequency decreases with time. So the one is called up chirp, one is called down chirp. Okay, you can have either way. So this leads to a frequency increasing with time, and so I want to estimate. So if I plot the frequency versus time, it will look like this. So let me plot this as omega tilde minus omega. So this is so it will go like this. Sorry, this is omega tilde minus omega versus time. So leading edge omega tilde is less than omega, trailing edge omega tilde is more than omega. So I want to calculate this increase in spectral width because of chirping, which is given by this approximately. Let me calculate this quantity approximately. What is this number? How much is this? Yeah.
There is instantaneous frequency is really a measure of the width of the pulse, the spectral width of the pulse.
No. Spectral width of the pulse depends on tau naught, the actual width of the pulse in time domain.
That is for Fourier transform limited pulse.
Always.
But in general for chirp pulses, when we are calculating omega tilde, that is, I mean, we are saying that it is less than omega, and afterwards in the trailing, as the later part of the pulse approaches, it becomes greater than omega.
Yeah.
So
instantaneous frequency.
Yeah.
This is the instantaneous frequency which was constant with time within the pulse at the input. Now is changing with time within the pulse itself.
So for this chirp pulse,
it has also a spectrum.
If you wish to calculate the spectral width,
then
you have to subtract these two peaks.
No. We have to actually take a Fourier transform of the electric field distribution and calculate. But I just want to know how much is the kind of chirping that this is creating. What is the frequency variation within the pulse?
No, but ideally what should happen is that the highest frequency minus the lowest frequency should ideally give us just the spectral width. No, I'm not saying about the constituent frequencies, different frequencies. I'm just saying that if you wish to calculate the spectral width, we can just subtract the value of the upper peak and the lower peak.
See, the problem is, in this pulse, the frequency remains constant with time. So I can't say that the spectral width of the pulse is 0. It is omega, delta omega of the order 1 by tau naught. So this is only an indication of what kind of chirping I have generated within the pulse. How much of chirping? The instantaneous frequency, if it remains constant, the pulse has a certain spectral width. If I keep the same temporal width of the pulse and now chirp the pulse, the spectral width will increase. So I'm sort of estimating from this quantity, because this quantity must be finally related to the increase in spectral width. If this quantity is 0, if N2 was 0 for example, then this is not there and it has a certain spectral width. Instantaneous frequency does not change with time. The presence of this term now, which means there is chirping in the pulse, tells me that the frequency spectrum has increased, and the increase in frequency spectrum must be related to this quantity here. By how much? I'm not telling this is exactly the increase in spectral width, but I'm saying that this is an indication of how much is the increase in spectral width that I'm going to see because of this. So if this quantity is much bigger than delta omega, which I've calculated, then obviously this is the spectral width. Otherwise, it is related to the total spectrum. Okay, so what I'm trying to do is only from this quantity guessing or trying to find out how much is the increase in spectral width because of the nonlinear effect. Now, how do I calculate at what time will the frequency be maximum and what time will the frequency be minimum? Can you calculate and tell me? What is the value of t at which the frequency is maximum and what is the value of t at which the frequency is minimum? What is this time and what is this time? Tau naught? Yeah. Plus tau naught by 2, just differentiate this equation and put it equal to 0, and you will get at t is equal to plus tau naught by 2 and minus tau naught by 2, the frequencies are maxima and minima. So let me try to calculate what is this maximum frequency within the chirp. So omega max within the pulse is omega plus omega by c and 2z 4 by tau 0 square. So t is tau naught by 2 I naught exponential minus half. Okay, so if I call this delta omega, which is equal to omega max minus omega, is of the order of omega by c and 2 z 4 by tau 0 square. So sorry, so this goes out 2 by tau 0 I naught by 2. This is just an estimate of the chirp that is taking place within the pulse. So the frequency will go from omega at the center to omega plus delta omega and then go back to omega, because the instantaneous frequency goes back to omega. And similarly on the other side, on the leading edge, it goes from omega to omega minus delta omega and then goes back to omega again. Because these are the peak values within the pulse. There are two positions where the frequencies are maxima and minimum with respect to the chirping. So let me put some numbers and calculate how much is this quantity. Okay, so let me calculate also delta nu. So delta nu is equal to delta omega by 2 pi, the actual frequency. So this is nu by c n2 z into 2 by tau naught I naught by. Nu by c is actually 1 by lambda naught, the free space wavelength, and 2 z by 2 into z by tau naught root. So let me take silica glass. So 3 10 to the minus 20 meter square per watt. Let me take a pulse which is 1 picosecond, 10 to the minus 12 seconds. Let me take a length of 1 kilometer, which is 10 to the power 3 meters. And let me assume a wavelength of 1 micrometer, which is 10 to the minus 6 meters. And let me assume a power of say 5 watts, an area of cross section which is 100 micrometer square. These are some numbers typical of optical fibers. If you launch light into an optical fiber, the cross sectional area of the beam is about 100 micron square, and I can launch 5 watts of power into the fiber. So that will give me an intensity. I need an intensity here, peak intensity value. So this is the peak power of the pulse. That's the area of the pulse, area of the cross sectional area. So let me substitute here. So delta nu is equal to 2 into 3 10 to the minus 20 by 10 to the minus 6, 10 to the minus 12 into 10 to the power 3 into 5 by 10 to the minus 10, 1 by root 2.7 approximately. Can you estimate how much is this? So root 2.7 is about 1.65 something. So I can actually I can strike this off with a factor of 2 here. So you'll have 2 into, so 5 into 10, so into 10 to the power minus 20 plus 4 minus plus 18 plus 10. Something like here. Oops. Yeah, 2 10 to the power 12 seconds, inverse. Hertz, actually. That's 2 terahertz. What is the spectral width of a 1 picosecond pulse? About a terahertz. Okay, 10 to the power minus 12 seconds. So its delta nu is about 1 by 2 pi of 10 to the power 12. So about 1.6 10 to the power 11. Okay, so this is broadened much more. Spectral width is broadened much more. So what is the change in wavelength? What is the spectral width in wavelength space now? How do I calculate? So delta lambda is equal to lambda by nu into delta nu, which is equal to lambda square by c into delta nu. So this is 10 to the minus 12 by 3 10 to the power 8 into 2 into 10 to the power 12. So that's about 0.6. Nanometers. Okay, so what is the minimum width to which this pulse can be? Suppose I assume that this is the spectral width of the pulse, 2 terahertz. So if I have a pulse with delta nu is equal to 2 10 to the power 12 hertz, this corresponds to delta omega of the order of 2 pi times this. So that's 12 into 10 to the power 12 radians per seconds. So what is the minimum pulse width to which this pulse can be compressed? Is of the order of 1 by delta omega, which is 1 by 12 10 to the power minus 12 seconds, which is about 0.1 picosecond. Okay, so what is actually happening is, I start with a 1 picosecond pulse, propagate through this medium, it remains 1 picosecond approximately, but its spectral width increases because of this self-phase modulation. Because of nonlinear effect, the 1 picosecond pulse which was launched has increased its spectral width. Delta omega at the output is more than delta omega at the input. Now once I have a broadened spectral width, in principle actually I can compress it to a width of the order of 0.1 picosecond. So this is a very standard technique used in pulse compression. You start with a pulse, use some effect, nonlinear effect, to increase the spectral width of the pulse, and then compress it. Now how do I compress a pulse like this? Look at this pulse. This pulse has, let me show another figure. Okay. This pulse has a frequency spectrum like this, varying like this. So you have a pulse coming in, leading edge has lower frequencies, trailing edge has higher frequencies. Okay, so let me draw. So these lines, so this is a higher frequency, so the pulse is going like this in space. This is higher, lower frequency, higher frequency. Leading edge is lower frequency, trailing edge is higher frequency. Now how do I compress this pulse? I must pass it through a medium in which the higher frequencies travel faster than the lower frequencies. So what will happen is this will get compressed. This portion of the pulse should travel slower compared to this portion of the pulse. So leading edge is slowed down slightly, the trailing edge is made faster, and the pulse will compress. So I need a medium in which there is a strong dispersion. I can use a medium in which higher frequencies travel faster than lower frequencies, and appropriately, if I choose the length of the medium or whatever it is, that dispersion, because if the velocity of the light depends on frequency, it is dispersion. So I need to achieve a dispersion which can help me to compress this pulse to the smallest width possible. And so people use a pair of gratings, appropriately chosen gratings, to compress a pulse which has a higher spectral width. So you have a nonlinear medium first increasing the spectral width, and then you use a dispersive element to compress the pulse. So what you're doing is essentially you have you are not generating energy here. All you're doing is redistributing and making it compressed. So the peak power will increase. If there is no loss, the peak power will increase, the spectral width will decrease. So in many applications you need pulses which are tens of femtosecond long. This is 100 femtoseconds. 0.1 picosecond is 100 femtoseconds. So actually you can use this pulse compression technique if you have an appropriate medium which introduces a lot of nonlinear effects. I increase the spectral width by using a nonlinear effect, and then I use dispersion to compress the pulse. So this is one standard technique which is used for pulse compression, and that is based on the surface modulation. Now, what we will not discuss is more details of surface modulation, which actually lead to the concept of what are called as solitons. So I left it as a possible term paper for all of you. You can actually use this nonlinear effect to generate pulses of light which will not disperse as they propagate through the medium. Normally, if you launch a light pulse into a medium, because the light pulse contains many frequencies, and because each frequency travels with a different speed, the pulse which is launched actually becomes broader in time. So if you launch a 1 picosecond pulse, it may become 2 picoseconds, 5 picoseconds as it propagates through the medium. Because this 1 picosecond contains a spectrum of frequencies. Some frequencies travel faster, some frequencies travel slower, so effectively the pulse gets broadened. So this is called dispersion. This is a very important effect in optical fiber communication, because in communication you use digital signals and those signals start to overlap. There is interference between adjacent pulses. You can use this nonlinear effect to overcome this dispersion. The chirping is playing a very important part there, so I will not discuss that. So these pulses which do not disperse as they propagate are called solitons. And this is a very important area of research in many, in communication, and also there are soliton lasers and so on. So actually, you can also use this to overcome diffraction. If you launch a light beam, it diffracts because of diffraction. You can have sufficient power in this to use surface modulation to compensate for diffraction. So soliton, temporal soliton, is a pulse of light which propagates without dispersion in time. A spatial soliton is a beam of light which does not suffer diffraction in space. It's the same problem. One is in time domain, one is in spatial domain. So diffraction in spatial domain is something like dispersion in the temporal domain. The pulse broadens in temporal domain, the beam diffracts, becomes wider in the spatial domain. So you can use this effect to overcome the broadening in time domain, leading to what are called as temporal solitons. You can use this to overcome diffraction in spatial domain, which is called a spatial soliton. So these are very interesting effects, which we will not go through in detail in this course, but with this background that I have given here, it should be possible for you to use this background to understand some of these features. So do you have any questions on this? Otherwise, I'll just introduce what we are going to talk next, and then which we will discuss in more detail in the next class. Okay, so next what we are going to do is, instead of one frequency, I want to put in two frequencies. So what will be the effect of this? So P nonlinear is epsilon 0 chi 3 into the total electric field cube, E cube. So what is E? E corresponds to now E1 e to the power I k1z minus omega 1t plus complex conjugate plus E2 exponential I k2z minus omega 2t plus complex conjugate. This is the electric field of the omega 1 wave, This is the electric field of the omega 2 wave. Now, can you tell me, if I substitute this into this equation, what are the terms I will generate? What frequencies? For example, this into this, that is this square into this. What will that be? Omega term, which will be self-phase modulation. It will be of the form E1, E1 star, E1 star, into you will have exponential I, K1Z minus omega 1t. This is self-phase modulation, which we have just now discussed. It doesn't depend on the second frequency at all. So what will be the factor multiplying out? 3. 3a square b. A plus b plus c plus d whole cube. There is a 3a square b. Now I can also have, is there any other term at exponential I K1Z minus omega 1t? That's all right. Other than that, yeah. Yes. So I will have E2 star E1 I K1Z minus omega 1t. Because you have cancelled off by E2 star, you have cancelled off the time and space dependence. And all you are left with is the space and time dependence of E1. What will be the factor? 6abc. This is lead to a nonlinear polarization at frequency omega 1 because of the presence of omega 2. The light at omega 2 is changing the refractive index of the medium at frequency omega 1 of this light wave, and this is called cross phase modulation. It's called cross phase modulation because omega 2 frequency, the presence of omega 2 alters the propagation of omega 1. So omega 2 is leading to a change in refractive index as seen by the omega 1 wave. The first term is the omega 1 wave sees a change in refractive index because of omega 1 wave, self-phase modulation. This is the term in which the omega 1 wave sees a change in refractive index because of the presence of the omega 2 wave, and that's called cross-phase modulation. So if you launch two light waves into the medium, you can actually alter the propagation constant at omega 1 by changing omega 2. So if I launch, for example, a very weak beam at omega 1, and if I change the power of omega 2, I will change the phase of omega 1. Because the refractive index as seen by omega 1 now also will contain a mod E2 square even term. So I can actually modify the refractive index of the medium at a particular frequency by using another wave at a different frequency, and this is used in optical switching. I can use this effect to switch light at omega 1 from one port to another port by using interference effects. Okay, we'll stop here. I will also come out with another term here, which is a very interesting term, which is called the four-way mixing term, and we will not discuss much more detail of cross-phase modulation, but the four-way mixing we will discuss a little more detail because as you can see here, this is already self-phase matched, right? The four-way mixing term we will see is not phase matched automatically, and I need to do something to phase match that term, and we will discuss that because that has also important application in quantum information, because people use this effect, this four-way mixing effect, to generate non-classical states of light using this process. Okay? Okay, thank you.